Previously, we saw how point charges can place forces on one another through the electric force and generate electric fields. So essentially, we were looking at point charges and calculating the electric field due to each point charge. And we could then say that the force on a second charge would be equal to the charge of the second charge times the electric field. So this was fairly straightforward in doing these calculations. Again, we could use Coulomb's law, F equals K, Q1, Q2 over R squared, or we could alternatively calculate the electric field, E equals K, E, Q being the charge that's producing the field, and then again, R squared being the distance to the point that we're measuring the electric field. Of course, if we have more than one charge, the superposition principle just tells us that we'll just add the effect of each electric field together to get whatever the result is. So for instance, if I wanted to find out what the electric field was at this point, I would calculate the electric field due to this charge. So we'll call that E1. And I calculate the electric field due to this charge. I'll call that E2. Actually, it's negatively charged, so it would be pointing in the opposite direction. And I just add the vectors together, and that would give me some resultant. I can do this with as many charges as I want, up to an infinite number of charges, and determine the electric field at any point in space. Now, what happens when we have a distribution of charge? Meaning that instead of a point charge, and I know that these are spheres, but essentially they act like point charges. What if we have a long line of charges? How do we handle these cases? Well, this is where calculus comes into play. And calculus allows us to actually take many infinitesimal objects and sum them together. So for instance, if I had some long bar of charge, okay? Let's say that this long bar represents some distribution of positive charge, where the positive charge was lambda, which was the total charge divided by the length of the rod. Not important at this point, but we'll come back to that idea. Now, I can imagine that this bar is made of an infinite number of points, or an infinite number of point charges, where I can take the effect of each individual charge as I take segments of this bar. We'll call this little segment delta x, and I'm going to make delta x smaller and smaller and smaller. So the number of charges is getting larger and larger and larger until delta x goes to 0. And essentially, the number of charges goes to infinity as we approach that infinitesimal limit, okay? We know this in calculus to be an integral. So for instance, if I wanted to find out the electric field at that point in space right there, I could integrate over all the infinitesimal little segments that this bar would be made up of, okay? As long as I have a function that tells me what the distance is, distance squared, what the individual charge per unit length is, okay, I can effectively determine what the overall effect is. Because again, if we think about superposition, the superposition principle, we're just adding together a number of individual charges. Now, in this particular case, we're going to the case where we've broken it up into an infinite number of pieces, so each piece is infinitesimal in size. Now, we can do this for a linear charge. Let's say we have the length of charge, like in the previous case, where we're going to say, I'm going to break up each individual charge into a little charge called dq, where dq will be some charge per unit length times the infinitesimal length. If I have a two-dimensional object, I can say dq is the charge per unit area, sigma, times the infinitesimal area. And likewise, if I go to 3 dimensions, I can take the rho, which is the charge per unit volume, times the infinitesimal volume. So that's what I'm going to do with our equation. I'm going to rewrite Coulomb's law for electric fields like this, and I'm going to replace E with dE and Q with dq. Again, it's just written a little bit differently. KEQ over r squared. I've simply just plopped the q off to the right and taken an infinitesimal version of that q. Okay, so what I need to do is I need to take this equation right here and I need to integrate it along some line, along some area, or along some volume. Okay, now let's take the case of a line of charge. That's the first example that we're going to use. And again, we're going to say here, dq is going to be equal to lambda times dl. All right, so lambda times dl. So I've replaced my dq with that lambda times dl, and you can see that right there. Okay, now again, I don't just want the electric field due to one infinitesimal spot, okay? That would be just due to this little length right here. I could calculate what that electric field is, dE. I want to integrate from the top to the bottom. So I want to integrate over the entire thing, and that will give me the electric field of all the infinitesimal parts of that linear charge together, and that's going to give me my total electric field due to that linear charge. Okay, now here's the problem. If I look at this R right here, R is not constant. R depends on where I am with respect to a position on this rod. So as I integrate, my R's are going to become different. So my R squareds are all going to vary depending on where I am with respect to the top and the bottom right here. So I've got to be a little bit careful when I do this integration. So now I'm going to say, all right, let's make some assumptions first of all. Let's first of all break this rod into equal parts, okay? I'm going to cut it right in half right here. And I'm going to restrict my electric field to only looking at the electric field component, which is in the x direction, okay? By symmetry, I would imagine that the electric field from the top half in the y direction will cancel out with the electric field of the bottom half in the y direction. So I won't have to worry about a y component. Okay, so I'm only looking at EX here, okay? I'm only looking at the X component of the electric field. Now I'm integrating over that X component to get the total electric field. Again, this will only work at the very center of the rod. If I'm a little bit higher or I'm a little bit lower, I have to calculate for both EX and EY. All right, I don't want to get that complicated with this. I want to show you a simple example. So I'm just, again, using symmetry to cancel out EY. Now we know that when we take EX, okay, or let's say DEX, the X component of the infinitesimal electric field due to this little slice right here, that is going to be equal to DE times cosine of theta, where cosine of theta is the cosine of that angle right there. All right. So now I've replaced my original DE, okay, with this expression right here, okay. Again, we'll see that it has some common aspects of what we saw earlier. We have K and lambda. K is the electrostatic constant, lambda is the charge per unit length. I'm only going from 0 to L over 2, okay, because I'm going to assume the electric field due to this part by symmetry should be equal to the electric field due to this bottom part right here. So that's why I'm going to put a little 2 out in front of here, saying that, you know, instead of integrating from negative L over 2 to L over 2, I can just take half the length and multiply by 2. Again, dq was equal to lambda dl. So dq has been replaced by this lambda and this dl. R squared is still in there. And again, because we're only taking the X component, okay, we're only integrating over the X component, we have that cosine theta right there. Okay, now let's make a substitute for R squared. By the Pythagorean theorem, if X is my horizontal position, Y is my vertical position, this hypotenuse represents R squared, represents R, and R squared would be X squared plus Y squared. Okay, so think about this. By the Pythagorean theorem, R squared equals X squared plus Y squared. So that's a fairly easy substitution that I can make. The other substitution that I can make is a little less obvious. I'm going to replace cosine theta. We know cosine theta is equal to the adjacent, okay, divided by the hypotenuse, which in this case, the adjacent side to theta is X, okay? The hypotenuse here is a square root of X squared plus Y squared. So I get a pretty complicated expression right there. So I'm going to take that and substitute that in right there. Again, substitute in for R squared. So now I'm looking at a fairly ugly integral here. Here's what my integral looks like. And again, let's just identify which part is which. That was my cosine right there. That's my R squared right there. Okay, but you know, I can combine those two expressions. And I know that this is X squared plus Y squared to the first power, okay? This is X squared plus Y squared to the 1/2 power. That's what the square root is. And 1 plus 1/2 is 3/2. So this becomes the final integral that I'm going to integrate, okay? And you can do a number of things. You can actually integrate this through substitution. You can look it up in an integral table. You find that the results of this is this expression right here, okay? Again, I'm not going to go through the actual calculus of integrating that out, but we know that we're integrating here, you know, in the y direction. You know, even though we took cosine theta, I think that gets a little bit confusing. And that's why we had dy here, because this little section dl is dy long in the y direction. So that's where that came from. Okay, so now let's do a little bit of canceling out. We can cancel out an x with the square power right here, okay? And we can get this expression right here. You notice x is in the denominator right here. And then, you know, substituting in for y squared, y is just equal to L over 2. You know, we subtract it when y is 0, that's going to give us 0. And this is our final expression right here. So that is the electric field at the midpoint, some distance x from a line of charge. Okay. Again, please note, this is only the electric field at that particular point. Any other point, we are going to have to calculate the y component also. But what's interesting is if we take this to the limit where where L, the length of this, goes to infinity, okay? Where L goes to infinity up there, this expression right here, you know, this is going to go to infinity at the same rate as the numerator. So this whole thing right up here, believe it or not, this is going to go to 1 for an infinitely long object. And what that is going to give us is basically an expression for the electric field due to a very long line of charge. We will find, I think I made a little mistake here because I didn't carry the 2 down here. But if we look at our next expression, we still have the 2. This is exactly what we're going to get in the next chapter when we apply Gauss's law using a cylinder around a line. If we take L to an infinite length, we know that KE is actually equal to 1/4 pi epsilon 0. And that's the exact same thing that we get here. So you will, again, find that Gauss's law is such an easier way to calculate electric fields sometimes, rather than dealing with these very difficult integrals, some of which are nearly impossible to calculate, okay? And again, here was this big ugly integral, and this is not the worst integral to solve for, but it's certainly not the easiest one either. And using Gauss's law just makes things easier. We're going to do the same thing for a ring of charge. This is actually an easier calculation to make. We are going to calculate the electric field at some point above the center of a ring of charge. And in this case, if we look at our geometry, Z represents the vertical distance that this point is above the ring center. R represents the radius of the ring. And phi is going to represent a direction going around the ring. Okay, that's important because we're going to integrate all the way around from 0 to 2 pi to complete the circle. Okay, so once again, we have our expression for a line of charge. I know it's a ring of charge, but for a one-dimensional object, okay? We are going to make a few substitutions. First of all, we're going to replace r squared, little r squared, with this right here, because that is my distance that this point is from any infinitesimal point on the ring. Okay, I am going to replace, sorry folks, I take that back. Getting ahead of myself. I'm going to replace r squared with z squared plus r squared. And I'm going to just take the z component of the electric field, which means I'm also going to have a cosine theta. And just like we saw before, cosine theta is the adjacent. In this case, it should be, big R. Okay, that should be big R divided by the hypotenuse. Okay. All right, so I combine r squared with the square root of z squared plus r squared, and I get, again, this crazy, similar to what I got before, z squared plus r squared to the 3/2 power, okay, dq. All right, got to make another substitution here, because how do I integrate over all these little infinitesimal dq's? Well, dq is lambda times ds. ds is a little segment of this ring, and each segment ds is r d phi, okay, where phi goes from 0 to 2 pi. So now I'm going to plug this in for where dq is, and I get this expression right here, okay? Again, I'm only going to consider the oops, I didn't want to do that. I'm only going to consider the z component here because, by symmetry, all the other components are going to cancel out. Now, what's much better about this integral than the previous integral is most of these things are constant. K is a constant, lambda is a constant, r is a constant, z is a constant, z and r are constants. So really, everything can be kicked out to the front of the integral except for d phi. So now what I'm going to do is I'm going to integrate from 0 to 2 pi.
Go 3.
And I'm going to take d phi, I'm going to integrate from 0 to 2 pi. That's really easy, right? Just becomes 2 pi minus 0. And just kick 2 pi in front of that equation. So that represents the electric field in the z direction. Okay, there's that 2 pi that's been integrated. The electric field in the z direction due to a ring of charge. Okay, and again, lambda here represents the charge per unit length. The length is the circumference, and you can either write the equation like this, okay, or it's probably simpler to write it like this, okay? That the electric field is equal to K, Q times Z. Q is the total charge of the ring, and divided by Z squared plus R squared to the 3/2. A little bit cumbersome, but that is the result that we get. Okay, let's kick it up another notch. None of these integrals, well, that integral was easy, but many of the integrals that we come across are not easy. And that's why the next chapter is so important for what we're going to do. Okay, again, we want to calculate the electric field at some point. How do we do that? Okay, we integrate over some infinitesimal point of charge. In this case, I'm going to take an infinitesimal area and integrate over all the area. In one direction, along the other direction, all the little infinitesimal areas are going to add up together to create one total electric field. So in this case, it just becomes dE equals K. Q is sigma dA, as we said earlier, over R squared. And then I'm going to integrate over the area and get whatever result I get. And again, sigma is usually a constant. If it were a function of position, then it becomes even more complicated. So usually sigma can get kicked out up front. Okay, so let's do an area of charge. We're going to go back to the ring of charge, which we did earlier. And now what we are going to do is we are going to take ever expanding rings and integrate from a ring of small radius to a ring of some radius, big R. Okay, so again, here's where I start from. I already saw that the cosine of the angle is going to be R over Z squared plus R squared. Okay, I already saw that R squared is equal to Z squared plus big R squared. Sorry, folks, these should be big R's. Okay. Oh no, I'm sorry. That's not a limit. That's not a limit. So we are using small r because we're going from a small radius to a big radius. Big R represents the overall size of the disk. So in any case, I get this crazy 3/2 power in the numerator. Once again, I'm going to substitute in for the infinitesimal amount of area here. If we think about a ring of charge, the area is equal to the circumference times the infinitesimal radius of that. So if we're looking at a little infinitesimal part of this disk, it's going to be dr by 2 pi r. Okay, so think about that a little bit. Okay, got to think about that a little bit. But in any case, plug that in. I do that integral. I get this as a result, and that gives me the electric field as a function of the radius. Okay. Now, what's interesting is, I know I'm leaving out a lot of calculus steps. I apologize for that. What's interesting is, if we take limit where big R goes to infinity, what happens to this whole expression? Well, that makes this go to infinity. That makes this term go away. And our result is just this right here. Now, that means that if I calculate the electric field from a plane of charge that's infinite, where again, R is going to infinity and beyond. I was forced to watch too many children's movies. We get the same exact expression that we get for a plane of charge according to Gauss's law. So we'll see that in the next chapter. Okay. If we have a volume of charge, you're just going to follow the same procedure. Instead of integrating along a line or over an area, we're going to do it over an entire volume. So we're going to look at all these little infinitesimal volumes that make up whatever object we're trying to calculate the electric field from, and again, come up with some expression.